Okay. Okay, good afternoon, everybody. Today we will talk about transformer model. So last time we talked about attention model, and as you remember, in attention model, we look at the encoder every time when we want to generate a new token. And now, so yeah, I will skip this. Yes. So this was one model when we used attention in the output from hidden state of our second recurrent neural network. There was, and because it's LSTM, it also has a state cell. So this attention was used as the state of input to LSTM. In this long model, oh no, wait, not as a state. Let's- From this image, it looks like a state, but I believe it's concatenation with decoder. In long model, it was used as concatenation with with output from before the logits. Okay, and these were attention maps. Okay, so in 2015, I think the paper which is still one of the most cited papers was written, "Attention is all you need." So in this paper, they proposed to use attention not only between decoder and encoder, but also inside decoder and inside encoder. And it's called self-attention. So let's look at the model. Oh, and the idea, like intuition behind this was that mm, sometimes we have homonyms when the same word has different meaning. Like in this case, bank. Which bank? Bank of a river or bank with money. So to even to if we have just word embeddings, uh, the word bank would have the same embedding. But in our sentence, word bank can depend on the context. And maybe we should look at the entire phrase to understand better which bank we refer to. So, yes, so in case of previous approach, recurrent neural network, we read just word by word and we don't see the entire sentence. But if we look at all the words, then it's better. And this is the idea of self-attention. So, um, I don't like this illustration. This is better. So, as you remember, we have at our input tokens, then tokens were passed through embedding layer. So these green blocks represent embeddings of our tokens. But then we want to look at all other words, and we create three different embeddings for our input embedding. So this image is not very accurate. Actually, for every input token, we create three embeddings. How do we create three embeddings? We just create three linear layers with different weights and apply three linear layers to our token embedding. And this is how we will get three new embeddings. You can think about this as different costume. For example, you can wear one costume for one event, another costume for another event. So in this case, the role of costume plays linear layer. So we apply, we create for example, linear layer 1 and multiply by our embedding. I will denote the embedding by X. Then we can apply another linear layer 2 and apply to our embedding X1. So we can denote this input as X1, X2, and so on. And another linear layer to X1. So we will get three different representations, three different costumes for the first, actually for each token. For each token, we will have three representations, and they're called query key and value. But for now, let's refer to these embeddings as blue, yellow, and red. It's easier, for me at least. Then we'll understand why they're called query key and value. So this is the first step. We kind of create three embeddings for every input embedding. After that, we will use which color? In this case, it looks like it's blue color. So we will use a blue embedding as attention. So from a blue embedding, we will calculate the dot product in the simplest way, or whatever attention score, with every yellow embedding. So let's finish our drawing. For this token, we also have yellow and red. Every token has 3 embeddings. So for each token, in this case for this one, we calculate the score, and also we calculate the score with itself. So it's not represented on this image, but we take the blue embedding for one token, and as you remember, we just multiply it on one matrix, then we take a yellow token multiplied by another matrix, sum up together, and or take just the dot product, so it's just a score. So we calculate this score from our current word with all other words and with itself. So we will get some one-dimensional numbers. After that, we apply softmax to convert these numbers into probabilities. And finally, and this is a new costume, we will sum up these words, but red embeddings. Finally, we will, so to calculate the probabilities, we use yellow embeddings, but to sum up, we use the red embedding. So we use yellow weights with red embeddings. And this averaging of red embeddings with yellow weights will be our new embedding. But now this new embedding kind of looked at every word in our input sentence. And we call this context-aware embedding. So, and yeah, this is the idea of self-attention. And we do this for every token. For the first one, take a blue representation, calculate attention with every yellow. It's hard to say because it's not because we calculate attention scores with every yellow representation, but we sum up these scores with red representations. And then we do the same for the second input embedding and so on. And in the output of this self-attention layer, we will get exactly the same number of embeddings as input, but they will be context-aware. So this is the idea. Kind of, in this example, you can see a red cat or a black cat. In this case, we saw a cat on a mat, not on the table. So this is the idea of self-attention. And now let's understand this terminology. Why blue embeddings are called query? What do you think? What we're doing to calculate this context-aware embedding. We take a blue embedding and calculate the attention score with every yellow representation. It kind of, this token asks other tokens how they are related to our token. So that's why it's called query. So this token goes to ask others. I don't like this actually terminology. I used to think about this just like 3 different embeddings, but it's a common terminology. So the yellow embeddings are called keys. Also, I don't know what is the reason to call them keys. So query asks keys, and then we sum up red embeddings cell, they called values. Maybe it makes sense because this will be the actual value of our output embedding. Yeah, and yeah, this is just one linear layer, another linear layer, the third linear layer applied to our input. So we get three different representations for our input embedding. And after that, we apply this self-attention mechanism. Let's write the formula to make it more clear. Hmm. Hmm. So much. So so now we will write self-attention layer, but we will call it attention. Attention layer will apply to three inputs. To query, key, and value. So again, this Q, K, and V are the let's see, columns or rows. Rows. So, for example, we have input tokens x1, x2, and so on. Then we apply three different linear layers, and we will get one matrix which is called Q. In matrix Q, we will have the first linear layer applied to x1, the first linear layer applied to x2, and so on. Then we will have the second matrix, which was yellow, another linear layer applied to x1, x2, and so on. And then we'll have a third matrix, values, when we apply a third linear layer to x1, x2, and so on. Does make sense? From one input matrix, we have three different matrices. One is blue, one is yellow, and the other one corresponds to the red embedding. Then what we are doing next, we take in the simplest case the dot product between every vector between vector Q and every vector in matrix A. So we calculate how to calculate the dot product between matrix Q and K. You can use Q times K transposed. As the result, you will get the dot product between Q1, K1, Q1, K1. The dot product between Q1, K2. And so the first line will represent the attention scores for the first input vector x1. Does it make sense? It's transposed. And so on. So this line, the first line, will correspond to the attention scores between our first token and other tokens. The second line will represent attention scores between second token and all other tokens. But this is just matrix representation. In other words, in the first line, we will have attention scores scores for x1. In the second line, we will have attention scores for x2. And so on. Scores for x2. So after we calculated the scores, we should take the average with the red embeddings, with values, with these scores. So what we want to have, we want to multiply these values with vectors from V. So how to do this? So we take this line of scores and and multiply it by the first column. If we multiply this line by the first column of matrix V, we will take the weighted sum of the first components of our vectors V. When we multiply the first line by the second column, we will take the weighted sum of the second components. So, but first we should apply softmax. Okay, let's write the formula, and maybe I will explain it later. So we take softmax of this Q times K transposed. Also, they normalize in the original paper by square root of the embedding dimension. And you remember we did this also when we, or on week 1, I believe, or no, on week 2, when we created an embedding for the sentence, because to preserve the variance, because if you calculate, if you assume that vector Q and K are normal vectors, then you will get the sum of normal Gaussian distributions, and the variance of the sum is the sum of variances. So if you add the square root, the variance of the constant will result in the squared constant. So the sum of variances will be d times variance, and the square root will go outside of variance as 1 over d. So d will cancel out and will preserve the variance. So this is the intuition why we should normalize by square root of d. And then after we normalized our line, our vector Q, we multiply this by the vector, the matrix V. And as the result, what we will get as the result. So if you multiply the first line this line with the first column, then with the second column, then with so on with the last column, you will take the weighted sum over all components. So as the result, you will have uh, the first vector. The first vector will be actually the embedding, output embedding from for the first token. Then when you take the second line and again multiply by this matrix over all first components or all second components and so on, you will get the vector which is embedding for the second token and so on. So this is just a short matrix notation for self-attention. Okay, let's go back to the slides. So yeah, and that notation that I used, of course, it works only when we use a score function dot product. If we use additive attention score, then we can't use that formula. But I hope you understand the general idea that first we create three different embeddings for each token, then we calculate the scores for this blue representation with all yellow representations, and finally we sum up the red representations with these scores. And we do this for every token. Oh, here is the formula. Mask self-attention. Well, as you remember, we I will erase the previous drawings. When we train our model, we actually know the true translation. But we don't want to so well, first of all, we introduce attention also in decoder, but in decoder we don't want to look at the tokens that we didn't generate. So that's why in decoder we will use so-called masked self-attention. So in this example, when let's say we generated two tokens, and then we will apply self-attention, but self-attention will look only at the previous tokens. We don't want that in decoder we look at the tokens that we didn't generate, didn't translate. Does it make sense? And this is called masked attention. When we calculate context-aware embeddings, but we look only to the previous tokens. And you can do this just multiplying by mask, and that's why it's called mask attention. Well, there is also idea of multi-head attention. This is on the example of the translation from Russian to English. Let's see. Okay, let's talk about multi-head attention. So when we create three embeddings, three different embeddings for our original embedding, we can split them into parts, and these parts are called heads. So, like when we create here three different embeddings, instead of using the entire embedding, we can, for self-attention, we can use just a part of this embedding. This part is called head. So, um, for example, on the first step, I will use only this part for self-attention. So I will calculate kind of smaller context-aware embeddings. Then I can calculate self-attention for the second part, and so on. So how many splits you will take, then you will have the same number of heads. So one head corresponds to the self-attention from the first part of your embeddings. Then you can apply self-attention to the second part of embeddings. It's called head 2, and so on. So in the original paper, they had 8 heads. In this example, there are 4 heads. So after that, you will have kind of 4 small context-aware embeddings for each token. And after that, you apply a linear layer, so concatenate all this and apply linear layer, and this will be the output embedding. So this is called multi-head attention. When we calculate self-attention on subsets of our original embeddings. The reason to use these different splits is that in practice, people notice that different heads learn different connections. So, for example, one head can learn punctuation or syntax. Another head can learn word and verb relationships, verb-subject relationship. So that's why typically multi-head attention used, not just self-attention. And this is formula for multi-head attention. So first we apply 3 different layers to our input embedding. So we have these 3 costumes, 3 different representations. Then we apply attention, the formula before, when we calculate scores and average with weights. And we calculate one head. After that, we concatenate all the heads and apply another linear layer, and this is the output impedance. Yes, and in practice, you don't need to apply, so for example, you have 4 heads, you don't need to apply 4 times three different layers. We apply one layer and then just cut our output in these four parts. Yes, here is the illustration. Okay, and now let's go to the transformer architecture. So this is how self-attention was drawn in the original paper. So if you look like from the beginning in this drawing, I think you wouldn't understand anything here. So this is part this part is encoder. So what is going on here? In encoder, we have input embeddings. Then we apply multi-head attention that we saw like on previous slides. And after multi-head attention, we use residual connections, skip connection, and apply so-called linear normalization. We in machine learning, we only studied batch normalization, batch norm. But in transformers, they use linear norm. The difference is between the batch norm and linear norm that in batch norm, we kind of have moving average to store information about mean and variance over. So it's kind of updating with every new batch. In linear norm, we don't have this like overall data set mean and variance. Mean and variance is calculated only for current batch. So this is the difference. And after that, we apply two linear layers, feed forward. And then we again use residual connection and linear norm. And then we have n, we repeat this n times, so kind of first we calculate this multi-head attention context-aware embeddings. Then we use these embeddings as input to induce multi-head attention, and so on. So typically 8 or 16 times we repeat this multi-head attention. So again, I will write the formula for this. So we have input sequence x1, x2, and so on, xn. And we want to get the output sequence y1, y2, and so on, ym. So for example, input is text on one language, the output is the translation. First, we calculate embeddings. I will denote this by h with superscript 0, h for 1, h2 for each token. Then we can kind of not concatenate, but combine this and denote this by a matrix H0. Then we apply self-attention. So we apply multi-head attention to what? To So Q is the linear layer applied to H0. So we apply one linear layer to H0 and we call it Q, for example. Then key and value. So these are blue, yellow, and red representations. And as the result, we have these context-aware tokens. Then we use skip connection. And then we apply normalization. Then after that, we apply feed-forward neural network. Typically just two linear layers. Then we add again this thing because it's kind of skip connection. And finally, we apply again normalization. So this is the formula for what is going on inside one block of transformer. And then we just repeat this n times. Okay, now we should wrap up. I just want to finish maybe that then we do the same for decoder, but we add mask, so that it's called mask self-attention. Then when we generate new token, we use the attention between decoder and encoder like we did with sec-to-sec last time. So 3 attentions, they result in this transformer architecture. And finally, the first part, we will study this next week, is called BERT model. When we just read the text and create context-aware embeddings. The second part, if you just take the second part, it's called GPT model, when we generate new tokens. And it's not used frequently. There was also large language model that combines encoder and decoder, C5. But we will talk about just these parts. Yes, and so next week we will talk about encoder of this transformer. Okay, that's it for today.